So last time we kind of did a little, hopefully some review-ish of redox reactions. Again, a reminder, we have oxidation, which means that we lose electrons. We have reduction, that gains electrons. We have the oxidizing agent that gets reduced. We also have the reducing agent. Again, that is the substance that gets oxidized. We talked about balancing redox reactions and also oxidation numbers. And remember, oxygen is a really good place to start. Usually it's -2, not in all cases, unless it's peroxide, then it'll be -1. A lot of times, if you do have kind of like we had in a number of examples there, sort of three elements, you could start with the oxygen, and that gives you -6. Go to the left and save the one in the middle there for the end, +1 for hydrogen. Overall, this has a -1 charge. And again, in this particular case, that would be a +4 for the carbon in this case. Remember that when we balance in acidic or basic conditions, we do use water to balance out oxygens. And we also need to add 2 H pluses for every water that we add to one side to the other side. Then we add some electrons. Remember that when those equations are balanced correctly, they should be balanced kind of in two ways. Again, just like a normal equation. You should have the same number of elements on each side of the arrow, opposite sides of the arrow. And it also should have the same overall charge on each side of the arrow. Again, they don't have to equal 0, the charge, but it does need to equal each other. Any questions on that there? All right, so let's just do one more here just to wrap that part up here. So why don't we balance this redox reaction in acidic conditions? A little dichromate and some oxalate, make some chromium-3 and the carbon dioxide. So take a few moments there, balance it up. Also identify what's being oxidized, what's being reduced. Okay, let's take a look, see how we're doing. So again, we're going to figure out maybe what's going on in terms of oxidation reduction. This guy we did last time, -2 there, -14, -2 overall. That means the chromium here is +6. Over here, -2 for the oxygen, -8, -2 overall. So that's like a 6. It's probably like a +3 there for the carbon, +3 for the chromium on this side, -2, -4, +4. So once again, we could just see pretty simply when we look at the chromium, it started at +6, which is over here. It ended at +3, which means it's moving in the negative direction. And that means that this guy is going through reduction. By default, this guy would go through oxidation. We could also see it there, starts at +3, the carbon, ends at +4, so it's moving in the positive direction. So it's going through oxidation. That would make this guy here, our dichromate, our oxidizing agent, and our oxalate here, our reducing agent. First off, any questions on how to identify all that there? All right, so we're going to split it off into some half reactions here. Chromium with chromium. And copper with copper here. Not copper, but carbon with carbon. All right, so we want to balance everything other than carbon and oxygen and hydrogen. So we do need to put a 2 there for the chromium. We also need to put a 2 there for the carbon. So now that we did that, we're ready to do our oxygens. We will need to add 7 waters to the top equation. Because we added 7 waters, we will have to add 14 H pluses so that we don't end up being short. On the bottom one, actually by putting the coefficient there for the carbon, it actually did take care of the oxygen, so we don't need any waters on the bottom one because we do have 4 oxygens on each side. At this point, we're ready for some electrons. Overall, we got a plus 14, a minus 2, so that's a plus 12. Over here on the right-hand side, we have a plus 6 and a 0, so looks like 6 electrons for the top one. On the bottom here, that's a negative 2, and this is a 0, so a couple of electrons there on the bottom should do it. Also, does make sense since this is our oxidation, this is our reduction half reaction. We are adding the electrons to the correct side. In this particular case, we actually just need to multiply the bottom equation by 3. So I'm just going to rewrite both of them. So 6 electrons plus 14 H pluses. Dichromate. Couple chromiums and some water there. And bottom one, I'm going to multiply that 3 across. Got like an extra little minus 2 there. There we go. So doing that, 3C2O4, 2 minus, 6 CO2, and 6 electrons. Adding them together, electrons should always cancel out completely. And I think that's it. So 14 H pluses, a little dichromate, 3 oxalates, and 2 chromium 3s, 7 waters, and 6 CO2. Once again, this should be balanced in acidic conditions. We have 14 H's on the left, 14 on the right. 7 oxygens there, plus 12 more is a lot, 19. We got 12 oxygens there and 7 more is 19. 2 CRs on both sides, 6 C's on both sides. Overall charge here, plus 14, minus 2, minus 6. So that's a plus 6 overall, plus 6 over here. So we are good in both directions in this case. Once again, we know it's balanced in acidic conditions because we do see the H plus present. Any questions on this? Yeah. You add the waters to balance out the oxygens. So in this case, on the first one, we had 7 oxygens on the left there and none on the right. So that's why we needed 7 waters. We didn't need to add, if you're asking why we didn't add water to this one, we didn't add water to that one because we actually fixed it when we added the coefficient to balance the carbon. So by putting that 2 there, that gave us 4 oxygens on the right and 4 on the left, so we were balanced. If that didn't balance the oxygen, then we would have needed to perhaps add some water to the bottom. Other questions? All right, now that we again understand hopefully how to balance these guys, let's actually talk about what's in this chapter, kind of the main part of this chapter, and that is a galvanic cell. And a galvanic cell really is just a redox reaction, a oxidation reduction type reaction that occurs. These are the main sort of components to a galvanic cell that you could build in the laboratory. A lot of times you could do them in beakers. You'll actually do it in 24 well plates, but a lot of times you can use beakers to do so. We have one side of the galvanic cell is what is known as the anode side. And on the anode side of the galvanic cell, that is where oxidation occurs. So that is where the species gets oxidized. It's going to release electrons, and those electrons will follow a wire through a voltage meter to the other side in the other compartment. And in the other compartment is what we have known as the cathode, and that is where reduction takes place. So again, an oxidation reduction reaction, the anode oxidation, the cathode is where reduction takes place. So we usually have some type of solid electrode. In the case of this example here, it is zinc. And usually we will also have a solution that contains the ion version of the solid electrode. So in this case, we have a zinc sulfate solution that has zinc ions floating around and the solid zinc in here. On the other side, we actually have a solid copper electrode. And we also will have, as you can see here, a copper solution. In this case, we have copper 2 sulfates flying around or floating around. And that is your sort of cathode side of this particular reaction. So what happens in this process is the zinc will go through oxidation. And basically when it does so, it's going to lose electrons. And as it loses those electrons, what happens really to the solid zinc is it goes from the solid electrode and then decides to go into the swimming pool and go for a swim and become an ion at that point as it loses electrons. Those electrons, as I mentioned before, basically travel through this wire. Again, those electrons can be used to do some type of work, kind of like a battery when you put it in the battery compartment. And when it comes back over here, those electrons are going to come into the solution and it's going to hook up with some copper 2 ions. And it's going to cause the reduction of those copper 2s from copper ions to solid copper. And at that point, the copper is going to decide to get out of the pool, basically, and become a solid at that point. So we have this sort of process of losing electrons on the other side, gaining electrons. The cathode side you can kind of think of as being a little bit more positive, if you will, kind of pulling those electrons, negatively charged electrons, to the other side. Another really important component of a galvanic cell is actually the salt bridge. And the salt bridge in this particular picture here is traditionally a tube that basically connects both beakers, the cathode side and the anode side of the reaction. The salt bridge is pretty much filled with a salt, hence the name. So some type of ionic compound that's in there. In the case of this example here, we have potassium chloride. And what ends up happening is the chloride starts to head over here to the anode side. The positive potassium actually heads over to the cathode side in this case. You usually put some type of cotton balls there at the bottom of the tube so everything doesn't fall out, but it's able to kind of migrate through the cotton in and out and acts like a membrane. So why is the salt bridge sort of really important? The salt bridge is important because it allows really the function of this cell to continue uninterrupted. And just to demonstrate what would happen, for example, if you remove the salt bridge. So let's just say we had this sort of same setup here. We had our zinc electrode in our zinc solution and connected to our other side here. And this was copper, I think. Copper here and some copper 2 here. So in this particular case, what's going to happen is without, for example, the salt bridge being present, this system here will continue to go through oxidation. So these zinc guys are going to basically lose electrons and they're going to start heading this way. The result of that is you're going to get a pretty big buildup here of positive charge. And as these electrons come into the other side and take this guy out of the solution, what's left over here on the right-hand side is basically the spectator ion, which is negatively charged. So you have that negative charge like sulfate, for example, or nitrate or whatever it may be. So without the salt bridge, what's going to ultimately happen is you're going to get a buildup here of positive charge on your anode side, and you'll also get a buildup of negative charge on your cathode side. And that's not really good because you're trying to move negatively charged electrons to the other side. And what's going to happen in this case is now that you build up this big old positive side over here, there is no motivation for those electrons to go anywhere. They're just going to hang out over there on the left-hand side because opposites attract to each other. In addition, you also built up a much bigger negative charge on this side, which is also going to not make them want to go to that side. So the presence of the salt bridge, what it's able to do is really prevent the buildup of the wrong charge that you don't want. And that's why if you look at the example there on the other page, we have the chloride and negative ions filtering into over here on the left. And what that's going to do with those negative ions coming in is going to prevent the buildup of that big positive charge over there. We also have the positive ion flooding back in onto the right, and that's going to prevent the buildup of the negative charge. So the salt bridge plays a really important function to allow really the sort of separation of charge that you really need for this cell to continue to function, which ultimately is a little bit more positive on the cathode side and a little more negative there on the anode side. And that's going to keep the electrons now happy, because now they're going to want to kind of roll to the other side, where it's a little bit more positive, and away from the anode side where it's a little bit more negative. So that is the function of the salt bridge, to keep, like I said, the buildup of charge correct in your galvanic cell, and to keep those electrons flowing. Any questions on that there? So as I mentioned, we can look at the half reactions here, and what we see is when we look at our zinc, it goes from 0 to +2, becoming more positive, going through oxidation. And on our cathode side, those electrons are going to come in, going to add to our +2 here, and reduce it down to solid copper, giving us the net ionic equation of what's going on here. Zinc is going from 0 to +2, copper is going from +2 to 0, all a result of basically the zinc in this case sending some electrons over to the copper in this particular case. Any questions on salt bridge there? Galvanic cell. So you do need to know the main parts of a galvanic cell and sort of their function. Now, there is, as I mentioned, this sort of difference in cell potential between the sort of anode side and the cathode side, and that is what is sometimes referred to as the cell voltage, or the electromotive force, EMF, or the cell potential. Essentially, if you're asked to calculate any of those things, the cell voltage, the EMF, or the cell potential, you're basically being asked to calculate the voltage of that cell is really what they want you to do. A volt is equal to 1 joule divided by a coulomb. Coulomb is a unit of electrical charge. And again, as I mentioned, there's sort of that potential difference between the anode and the cathode side that keeps those electrons moving. Here's one you could build in the lab. And again, you can kind of see that is our salt bridge right there that connects those two. Here we have some positive voltage, which is pretty good, as we will talk about. Now, there is sort of a shorthand that can be used for galvanic cells, and that is what is known as a cell diagram. And in a cell diagram is sort of a shorthand description of the galvanic cell that's being run. It is always sort of written like this. It is always the anode first, followed by the cathode. So it's always the anode to the cathode. This is essentially the oxidation happening here. This going from 0 to +2. This is the reduction happening here on the copper side, +2 to 0 in this particular case. The two lines here represents the salt bridge. The single lines are basically the difference in the compartment of the reaction that's occurring. How do you turn like your cell diagram into an equation? Typically speaking, this is sort of how it goes when you look at a cell diagram. It is typically speaking reactant followed by product, reactant followed by product. If you had to kind of turn it into an equation, as you can see here, zinc reactant, zinc with a +2 product, copper with a +2 reactant, copper with no charge, a product. So again, that is typically how you can turn that into an actual equation. Other things that you sometimes will see in a cell diagram, you'll sometimes see concentrations. So that is 1 molar for our solutions. That is standard concentration. So if you remember, standard conditions is 1 molar for concentration. Also, if you're dealing with pressure, 1 atmosphere. That also sometimes is seen in a cell diagram, and that is because there are certain sort of electrodes, if you will, that are gases. And because of that, there's not really a solid version of it that you could use as a solid electrode. So a lot of times when that's the situation, they will use some type of carbon type material, graphite. They may use platinum, some type of a metal that really won't sort of conduct too much as sort of the physical sort of source of it. So sometimes you'll see those other things in these cell diagrams, pressures. You also sometimes, like I said, see some metals and stuff like that that's used as the physical sort of electrode. So let's talk a little bit about standard reduction potentials. Standard reduction potentials are sometimes abbreviated as an SRP value. That stands for standard reduction potential. Standard reduction potentials are all these reactions that we will see, and they're all written as reduction reactions. So it's a big table of reduction reactions that are occurring. Remember that when we write reduction reactions, that is like the electron on the reactant side, basically, when you look at the half reaction. And they will have a sort of E value or a cell voltage that is based on it. Here, when we look at this galvanic cell setup, we have zinc here as our anode. And in this particular case, we have a hydrogen electrode that's acting as our cathode. And as I mentioned before, because hydrogen is a gas, we may use something like platinum as the actual physical electrode in the galvanic cell. And you can see it here in the cell diagram. Reactant, product in this case. And again, we do see pressure here, and we do see a little extra addition of platinum, which again is serving as a physical electrode in this case. In this case, once again, our zinc is going from 0 to +2, so it is losing electrons and being oxidized. Here it is the hydrogen that's going from +1 to 0, becoming more negative, and it is going through reduction in this particular case, giving us again our overall reaction on the bottom. This is all under sort of standard conditions. All the pressures are 1 atmosphere, and all the concentrations here are 1 molar. Now, these standard reduction potentials are the voltages associated with the reduction reactions. And much like in chemistry, a lot of times what they will do is basically assign something as a standard to compare everybody else to. In the case of SRP values, they use the actual hydrogen electrode as the standard to use to compare everybody to. It is sometimes referred to as the She for standard hydrogen electrode, and that's sort of the standard that they use to compare everybody else's SRP values to. They arbitrarily gave it a value of 0 volts. So the standard hydrogen electrode has a value of 0 volts. And again, this is the SRP reaction. It again is a reduction reaction as we have our electrons there on our reactant side. So basically what they did is they hooked up this electrode, this standard hydrogen electrode, with a bunch of other sort of electrodes. In this case, that's our zinc and our hydrogen electrode. They got the cell voltage, and for this particular cell voltage, when they hooked these two guys together, they got 0.76 volts. Now, they could use this equation here to help them figure out what is the standard reduction potential for zinc. And this equation here is E of the cell is equal to E of the cathode minus E of the anode. Now, this equation here should be used when you decide not to change the sign of the value you find in the table. Now, if you want to change the sign, you then should actually add rather than subtract. And again, this may not make sense right at this point, but we will see them a bit here, or hopefully it will make sense. So just keep this in mind that if you use this particular equation, you should never change the sign of what you find in the table. You should use it exactly the way it is, and the equation here will actually change the sign for you. If you want to change the sign yourself, you need to actually add these together and not subtract. So that's an important sort of distinction. So when they do that and they hook it together, they get the SRP value here. Again, also a reduction reaction for zinc as minus 0.76 volts. So here is a table similar to one that you have in your book. And if you look at this table, every single one of these are written as reduction reactions. And again, they all have the electrons there on the reactant side. So what I was talking about a second ago is we have this equation, which is E of the cell is equal to E of the cathode minus E of the anode. And let's just say we took copper 2 as our cathode. And let's just say we took zinc as our anode in a galvanic cell that we basically put together. So what we would do in this particular case is we would go to this table and find those two. And if I do here somewhere, where is that copper? There's copper 1, copper 2. There it is. So here is the copper 2 sort of SRP. So it's copper 2 plus a couple of electrons goes to copper. E is equal to 0.34 volts. And if we look on the table there for zinc, zinc is a little bit down lower that we just saw. Our zinc plus a couple of electrons gives us our zinc, and our E is going to be negative 0.76 volts. All right, so now that we have these, let's talk about what we should do with these situations. So if I did in my made-up cell here and wanted my copper to be my cathode and my zinc to be my anode, one of these reactions actually is written incorrectly for that. And we know that at the cathode, that is where reduction occurs. And we know at the anode, that is where oxidation occurs. So for the copper, it actually is written correctly. That is written as a reduction reaction, which is what I'm looking for. But when I look at the zinc, I actually want it to be my anode, which means oxidation is really what it should happen. And the zinc here is written as a reduction reaction, which means technically speaking, I would actually have to flip the equation that I found for zinc in the table and flip it into an oxidation reaction, which would look something like this, and it would actually flip it. Now, if you flip this and wrote it as an oxidation reaction rather than a reduction reaction like you find in the table, what will happen to the sign is the sign will actually change from negative to positive 0.76 volts, because basically I just flipped it around. These are actually the correct overall reaction, which we could add together just like we're kind of doing redox reactions By the way, the electrons should always cancel each other out. And that will give us our overall reaction of zinc plus copper 2 is going to copper plus zinc 2. Now, if I wanted my E of the cell in this particular case, I could take my cathode minus my anode. And if I were going to use the formula like I just saw there with the subtract sign, I would actually want to use the value that I find in the table without changing the sign. And that is because the anode one is always the one that should change the sign. And that's actually what the subtraction is there for, to change the sign for you. So if you do that, you would go, E of the cell would be 0.34 volts minus a minus 0.76 volts. And again, that is what the subtraction button is actually there for in the formula. And you would get, obviously, our cell voltage in this particular case of 1.1 volts, which is a positive number. So if you're going to use this formula like it is here, which is a common way of doing it, the reason the subtraction is here is because the anode reaction is always the one that needs to be reversed. So that subtraction will actually change the sign for you. Now, if you want to technically change the sign yourself, perfectly fine. The only difference is you should not subtract. You actually have to add the numbers together. So if you wanted to just change the sign yourself, you then should take cathode plus the anode, where you change the sign that you find in the table. And you would do what I did over there, which was 0.34 volts, plus I already changed it to positive 0.76 volts. That's going to give us our 1.10 volts as well. So I would recommend, either way is fine. I personally use the minus one most of the time, but if you want to use the sort of adding, all you have to do is remember you do have to change the sign that you find in the table. I would probably pick one way and stick with it, so you're not bouncing back and forth and like changing signs and then subtracting and undoing and stuff like that. So I would probably try to pick one way and kind of stick with it. Any questions on that? By the way, if you were asked to write the half reaction for the zinc in this galvanic cell, technically speaking, the correct value for the oxidation half reaction would have an E value there of positive 0.76. So technically speaking, the way the reaction is written, you should give the proper E value for it. That is also sometimes referred to as standard oxidation potential, because it's an oxidation reaction rather than a reduction potential. Any questions on that there? Okay. Let's see here. Maybe. Gonna flip. Yeah. All right, and let's just take a little closer look at this table and some of the important things that you find on the table. First off, the E value is written for the reaction as it is written. So as I just mentioned a second ago, technically speaking, if you were to write the oxidation half reaction, you really should flip the E value that you find. Now, how do you know if you're just told pretty much you're going to build a galvanic cell out of these two things? How do you know which one should be like your anode and which one should be perhaps your cathode? So if you're given really not a lot of information other than like, hey, you threw these two things together and built a galvanic cell out of them, the one that has the more positive E value has a greater tendency to be reduced. So if you have to choose which one you want as your anode or your cathode, the one that is more positive should usually be your cathode. And that usually will give you your kind of positive voltage in this case. Now, it's also really important, and that is something that people screw up on a lot, which is they always just go with the more positive one. If you are given in the problem words that tell you how the reaction is happening, or you're actually given an equation or a reaction, you then should look at the reaction and see who's being oxidized, who is being reduced to decide what your anode and cathode is. In the lack of any information other than you just built the galvanic cell out of these two things, then you should go by the one that's more positive, would be your cathode. But if you're actually given the reaction, you do need to look at it and see who's being oxidized, who's being reduced to decide anode and cathode. So that's a big mistake. Sometimes people make a lot. The half reactions are reversible. If you reverse the half reactions, the sign of the E then changes. And one thing that is not affected is sometimes you do have to add or multiply a half reaction by a common number to get the electrons to be the same, right? As we talk about with half reactions. It will have no effect on the E value. So if you need to multiply a half reaction by a common number to get to the right number of electrons for everything to cancel out correctly, you do not multiply the E value by that number. So it is unaffected by it. So you don't want to do that. Any questions on that there? All right. All right, so why don't you give it a go here? Why don't you write the balanced equation and also calculate E of the cell in this case, yeah? So give it a go there. Some SRP values given to you. Galvanic cell out of cadmium and chromium. We would go to the SRP table there to find these, by the way. And in this particular case, we're not really told how it's reacting. So we could use our values that we find in the table to decide what will be our anode and our cathode. And in this case, our cathode should be the cadmium as it is more positive. And this would be our anode in this case. With that being said, since we're looking for the balanced equation, the anode one is technically the one that needs to be reversed. And we would then reverse this to Cr3 plus and 3 electrons. That E would technically then become a positive 0.74 volts. By the way, we also need the same number of electrons in each. So we do have to multiply this by 2. And that's going to turn us into 6 electrons. For our cadmium, we need to multiply by 3 to get us 6 electrons. And again, a reminder that multiplying does not have an effect on the E here. Once again, just like a normal sort of redox, electrons should completely cancel out. This gives us our overall reaction of what's happening here. And once again, at this point, you do have two options. Since I actually changed the sign of my anode, I could calculate E of the cell by adding those values together. The one where I already changed the sign of it. And that's going to get me 0.74 plus negative 0.4, a 0.34 volts. Or you could use E of the cathode minus E of the anode. And if I'm going to use that one, again, I'm going to use the original values and not change any signs. So I would take my cathode of minus 0.4 volts minus a minus 0.74 volts. Once again, that's going to change the sign for me, and that will get me to my 0.34 volts as well. So again, as I mentioned, if you don't change the sign, subtract. And if you do change the sign, you should add. Yeah. Any questions on that? Positive voltage, as we'll talk about, is good. Yeah. So in this particular case, we weren't really given any information about how the reaction is happening. So the one on the SRP table that is more positive will typically be your cathode. So that would be how you decide. Other questions? All right, so let's try another one here. Galvanic cell consists of magnesium and silver. Calculate the standard EMF of this cell or the cell voltage. Okay, so looking at this one again, we're really not given any information about how it's reacting. So we can use the SRP values here. And again, here, silver is more positive. So that would be our cathode in this case, and that would be our anode in this case. And again, if we're just looking for the cell voltage, once you ID that, you can go right into this equation, cathode minus anode. And again here, I'm not going to change the sign. I'm going to let the formula do it for me. So minus 2.37 volts, going to get me a 3.17 volts for my cell voltage. If I was looking to balance the equation, I would have to multiply this guy by 2. And it would get me this. And once again, the E is not affected by multiplying by 2. Here I would have to reverse the bottom to turn it into an oxidation reaction. If I did reverse the bottom, technically speaking, that would then become a positive 2.37 volts. Here the electrons cancel, gives us our overall reaction that's taking place. And then obviously here, our E of our cell, we would actually just add since we changed the sign here, and that would get us 3.17 volts. So any questions on that there? Yeah. All right, so let's talk a little bit about cell potential, electrical work, and free energy. The work that can be accomplished as the electrons are transferring through the wire depends on the push behind the electrons. 1 joule of work is produced or required when a coulomb of charge is transferred between 2 points. And that basically means that the maximum amount of work you could do is equal to our delta G, or our Gibbs free energy that we talked about in the thermodynamics chapter. So a positive cell voltage is really good because it will lead to a spontaneous sort of process that's occurring. So there is a relationship between those. And let's talk a little bit about those formulas and the relationship. A couple of these here. Get all those things going. So the first one here is our delta G is equal to minus NFE. Delta G is our Gibbs free energy. N is the number of moles of electrons. Now, when we talk about the moles of electrons, it is the number of electrons that is lost by the oxidation, and also the number of electrons gained by the reduction. It's the same number. So what I mean by that is if something were to lose 2 electrons and somebody else were to gain those 2 electrons, the N in this case is actually 2. It is not 4, so you don't add them together or anything like that. So it is basically the balanced number of electrons in each half reaction is what the N value should be. F is Faraday's constant, 96,500 joules per volt per mole. And E of our cell is our cathode minus our anode. So that is how we calculate all that. Now, there is a relationship between E of the cell and the equilibrium constant, and it is this formula right here. E of the cell is equal to RTNF. R is the gas constant. That's the one that has energy in it. That is the 8.314 version of it. T is our temperature in Kelvin. N again is our moles of electrons. F is our Faraday's constant, and K is our equilibrium constant. If you want at 25 degrees, all these things reduce down to this formula here. 0.0257 volts over N, natural log of K. Or if you're more of a base 10 log, 0.0592 volts over N log. If you don't want to worry about these two sort of equations here, just remember this one and just put the numbers in. So it all works out the same. So if you just remember the first guy in the box there, E of the cell equals RT/NF natural log K. Just put the numbers in and you'll be fine. That's our trifecta of goodness here. If you know E of the cell, you could calculate the delta G. If you know E of the cell, you could get to yourself through the equilibrium constant. And obviously from the thermodynamics chapter, we could go from G to K as well here. Now, this is why, by the way, when we look at this equation, when we get a positive cell voltage, it is a good thing because F is a positive number, N is a positive number, and with that negative there, and the E of the cell is positive, it will turn our delta G into a negative number. And as we talked about with delta G, if it's a negative value, then the reaction is spontaneous. So positive cell voltage corresponds to a negative delta G, which means the reaction is spontaneous. And by the way, that would also correlate to a large value of K. If you have a positive E, negative G, that all should be going towards the product side. And then going towards the product side would mean you would have a larger value of K. The opposite is true if you have a negative cell voltage. You basically just got to flip everything around to get a positive, but you have a negative cell voltage. That negative cell voltage and the negative in the delta G formula there will turn the delta G into a positive value, which means the reaction will be non-spontaneous. And because it's non-spontaneous, it's going to hang out on the reactant side, you probably will have a smaller value of K. So again, all those things should sort of agree with each other if you're calculating it. Any questions on that there? All right. And again, that's what we were just talking about a second ago. They do all sort of correlate to each other, the K, the E, and the G. All right, so why don't you give it a go here. Calculate the delta G for this reaction. And is it spontaneous? There's some SRP values there on the bottom. Okay, let's take a look here and see. We want to calculate delta G. So delta G would equal minus NF E of our cell. So in this particular case, we have an equation we should take a look at. This is going from plus 2, 0, 0, and plus 2. In this particular case, it is the copper being reduced. So that's going to be our cathode, and this will be our anode. Once again, I'm going to use the subtraction version of that equation. So I'm not going to flip any signs. Now that I've identified which one is my cathode and my anode, putting my cathode in there, 0.34 volts minus a minus 0.44 volts. Going to give me an E of the cell here of 0.34 minus 4, 0.78 volts. My N in this case would equal 2. Remember, it is the total number of electrons being transferred. So again, we don't add those numbers together, so just one of those numbers. And I think that's everything we need. So our delta G in this case, minus 2. Faraday's constant, 96,500 joules per volt per mole. And our E of our cell, 0.78 volts. Again, the volts are going to cancel, the moles will cancel. Going to leave us in joules, and that's going to be 2 times 96.5 times 0.78. Looks like a negative 150.540 joules. Not point, just 150.540 joules, or 151 negative kilojoules, if we convert it to kilojoules in this case. Any questions on that one there? Yeah. The N is the number of moles of electrons. It is not, like I said, you don't add both half reactions. but you take whatever the balance number of electrons are in each half reaction. That's what the end value should be. Other questions? Here we have a positive cell voltage that yielded a negative delta G, which means this reaction should be spontaneous as well. All right, let's try one last one here. Will nitric acid dissolve gold metal to form gold 3? Cathode and our anode, in this particular case, our cathode is the nitric acid, by the way, and our anode is the gold in this case. It may be saying, why is that? It is because we are not going by Morse positive here. We're going by what the question says, which is, will nitric acid dissolve gold metal to form gold 3? That means these two guys should be on this side, and they are on opposite sides here, which means this one needs to be reversed, which then would make this one my anode. So again, a reminder that you do have to go by what it says in the problem, or if you're given the overall reaction. With that sort of worked out, hopefully, our E of our cell, E of the cathode minus E of the anode. Once again, I'm not going to change the sign because I'm going to subtract. So I'm going to take my cathode 0.96 volts minus my anode of 1.5 volts. That's going to get me a negative 0.54 volts. By the way, that is enough for me to know that this reaction is not going to happen, because if I throw it into my delta G, this negative along with this negative will definitely give me a positive delta G value, whatever that number would actually be. And that positive delta G, that negative E, all tells me that this will not happen. Yeah. Work. It's non-spontaneous, really. Question on that. So again, it's really important in this chapter to make sure you do read the question. And more importantly, a lot of people always ignore the actual equation that's given to you sometimes in the problems, and just go by the most positive. So a reminder again, most positive is only a situation where you are not told how it's reacting, you're not given an overall equation, then you go most positive as your cathode. But if you're given something like this in words, or like on the previous problem, you would have lucked out, but you should have looked at the equation like I did to see what's being oxidized, what's being reduced, to identify the cathode and the anode.